You know, for over a century, there's been this deep, nagging question at the heart of physics. It's a question that all the incredible success of quantum mechanics has never really answered. In this explainer, we're going to dive into that mystery by looking at a theoretical path that goes way beyond one of the most famous attempts to solve it.
So, what's the real problem here? Well, it boils down to this. What is actually happening down there at the quantum level? We're fantastic at predicting what we'll see when we run an experiment, but what does the theory tell us about reality itself, before we even look?
And that right there is the big information gap. Standard quantum theory, it gives us the math, the probabilities, the rules for what happens when we make a measurement, but it doesn't give us a clear, continuous story of what an electron is actually doing when we're not looking. It's kind of like having a perfect recipe that guarantees a delicious cake, but never tells you what the ingredients are.
And this lack of a clear picture is something that famously drove Albert Einstein crazy. In fact, when the physicist David Bohm came up with a theory that gave particles definite positions using so-called hidden variables, Einstein wasn't impressed. He felt it was just patching a hole. For him, a truly complete theory couldn't just be an add-on. It had to come from somewhere deeper.
And that's the perfect jumping-off point for a paper by Partha Ghose. It explores a really radical alternative. The main idea here is that maybe, just maybe, quantum mechanics isn't the fundamental story at all. Maybe it's just what emerges statistically from something else, something deeper, and maybe even a little more chaotic.
So the paper sets out to tackle the very same challenge that fueled Einstein's critique. It's asking, can we build a more complete theory, right from the ground up?
And let's be clear, the stakes here are pretty high. The goal isn't just a new interpretation. It's to build a physical model that has what we call a clear ontology, a clear story about what actually exists. And here's the kicker. This model shouldn't just assume the rules of quantum mechanics, it has to derive them from its own first principles. If it can pull that off, it might just make those classic quantum paradoxes completely vanish.
So how does the paper even begin to approach this? Well, it uses a really powerful method. It puts two different attempts to complete quantum theory side by side. This contrast allows us to see exactly where they differ, and why one might be a much deeper solution than the other.
First up is Bohmian mechanics, sometimes called the pilot wave theory. Now this is the one Einstein thought was too cheap, but you can see the appeal, right? It's so clear. Particles are real things, they always have a definite position, and they're guided along by a real, physical wave. On this surface, it seems to solve the reality problem head-on.
So, if it gives us this intuitive picture of particles kind of surfing a quantum wave, you have to ask, right? Why isn't this the standard view? What's the catch? Well, according to the source paper, it leaves two pretty big questions on the table.
And here they are, the two key gaps in the theory. First, to get the right answers, the ones that match experiments, the theory has to just assume that particles start out in a very specific arrangement, following what's known as the Born rule. It doesn't explain why that should be the case. And second, it totally leans into spooky action at a distance, making it a fundamental feature of reality. These two issues are really what justify the search for a deeper explanation, which brings us to the paper's main proposal.
And this brings us right to the heart of the paper's argument, a theory called stochastic mechanics. Instead of nice, clean, deterministic paths, it imagines a world built on a foundation of pure, structured randomness.
Okay, so what exactly does that mean? Well, picture a particle. Instead of it moving on a smooth path, imagine it's constantly jittering around, undergoing a random walk, kind of like a tiny speck of dust dancing in a glass of water. Stochastic mechanics says this isn't just some background noise. This fundamental, random motion is reality at the quantum level. And this is where the theory's real power comes in. It completely reframes the problem. Those core laws of quantum mechanics we all learn about, like the Schrödinger equation and the Born rule for probabilities, they're no longer the fundamental laws of the universe. Instead, they're shown to be the collective, statistical result of this deeper, random dance. The randomness isn't a bug to be fixed, it's the source code. This table really lays out the difference beautifully. In Bohmian mechanics, the basic reality is particles. Randomness is just something we don't know, our ignorance. And the wave function is a real thing, a guiding field. But in stochastic mechanics, the basic reality is the random diffusion process. Randomness is fundamental to nature. And the wave function, it's just a handy mathematical tool we use to describe the statistics of that process. It's a huge shift in what we consider to be fundamental.
All right, now that we have the main idea on the table, let's see what it does. How does this completely different framework handle those famous, long-standing paradoxes of quantum mechanics?
Let's start with the infamous measurement problem, that whole mystery of why the wave function seems to collapse whenever we look at it. Well, in this framework, it's not a problem that needs solving. Actually, the problem never even shows up. Why? Because there's only one universal law of this random diffusion for everything. The tiny particle and the big measuring device are playing by the exact same rules. There's no need for a special collapse rule for measurements. It's all just one continuous process.
Now, to get a handle on spooky action, we need to understand a really critical concept called contextuality. It's a proven fact of physics, and the idea is that you can't really talk about a particle's property, like its spin, in a vacuum. The value you get when you measure it depends completely on the context, on the entire way you've set up your experiment to measure it.
And this right here, this is the essential nuance of the paper's argument. That apparent spooky action at a distance isn't some physical signal breaking the speed of light. The paper presents it as a logical artifact. It's a ghost that appears when we make a mistake, when we try to apply classical logic and assume that particles have definite properties before we measure them. The world just isn't built that way. The weirdness isn't in the physics, it's in our outdated assumptions.
Okay, so there's one more big question for any quantum theory. How do we go from this strange quantum world to the normal classical world we actually see and experience every day? Well, the paper proposes a mechanism that acts like a continuous bridge between the two.
So this framework introduces a kind of quantumness dial, a parameter called lambda. This dial directly controls the strength of something called the quantum potential. That's the mathematical term that's responsible for all the weird quantum effects. You can think of it like a dimmer switch for the intensity of that underlying random jitter.
And you can see it right here on this chart. If you dial lambda all the way down to 0, the quantum potential disappears, and poof, you get regular old classical physics. But if you crank it all the way up to 1, you're in the full-blown strange quantum realm. And in between, you get a whole spectrum of behaviors. What this suggests is that there's no sharp, sudden cut between the quantum and classical worlds, but a nice, smooth transition.
So let's bring this all together. At the end of the day, what can we responsibly say based on the paper's argument? It's really important here to separate what the framework suggests from what's been experimentally proven.
What we can say is that stochastic mechanics offers a powerful and logically consistent conceptual model. It shows how quantum laws could emerge from a deeper reality. It gives us a plausible physical mechanism for that classical to classical transition we just talked about. And maybe most profoundly, it reinterprets the classic paradoxes not as weird physics, but as the result of us using flawed logic.
And this all leaves us with a final, really provocative question, one that gets to the heart of this whole theoretical shift. What if the universe isn't built on a foundation of deterministic laws at all? What if instead it's built on a fundamental structured randomness, and all the laws we observe are just the result of that beautiful underlying chaos?